Welcome to video 39 in our series on tensor calculus. In this video, we're going to introduce a very important new operator known as the gradient. Here we have a scalar field represented in a two-dimensional space. And that means that for every point in our space, there is an associated scalar value. We represent it this way. We have a function. This function f is a scalar function, which means the output is a scalar value. It's not a vector. And the argument of the function is our point p. So for every point p, there is an associated scalar value f. For review, you might want to go back and look at video number 3 again. Now, I've also drawn a path in our space, this yellow line here. And we have a point p on this line. And p is moving along this curve, and we'll use the variable s, which is just the distance along the curve, the arc length of this curve, as the variable to track where we are with our point p here. So point p traces out this curve using variable s as the parameter. Now, at this point, what we want to do is to investigate how our function changes as this point moves along the curve. In particular, we're interested in knowing what the rate of change of our function is with respect to the arc length ds. So what is the rate at which our function f is changing as this point moves along the curve? Now we call this expression a directional derivative. And we call it a directional derivative because it is dependent not only on our function, f of p, but also it's dependent on the path that we're moving. It's dependent on the direction in which we measure it. All right, if we're going to evaluate this expression, we first realize that our function f is a function of the point p, but if we're using a coordinate system, then we can also express it as a function of our coordinate value z, and then that z is also a function of s. So we can use then the chain rule to evaluate this. The derivative of f with respect to s would be equal to the partial derivative of f with respect to zi times the ordinary derivative of zi with respect to s. Now we have to use the partial derivative here because z is not just a simple variable, it's a set of variables. So we have to use the partial derivative. But here s is just an individual variable, it's the arc length, so that's why this is the ordinary derivative. Well, what do we have here? What we have is two factors. This one is looks like a covariant vector component. In fact, it is, because you remember when we take the derivative, a partial derivative of a scalar function, we get a covariant component. We've done that a number of times already. And this expression looks just the opposite. It looks like a term with an upper index, which would make it a contravariant vector component. We also notice that this is a contraction. We're using the same index here and here. So what we've got is a covariant vector component contracted with a contravariant vector component. And if you'll remember, that's nothing but a dot product. So what we have here is a dot product of two vectors. Well, what are these vectors? Let's see if we can figure that out. Now to do that, let's take the derivative of our position vector r with respect to s. And as with the function above, we'll use the chain rule. And we start with the partial derivative of our position vector with respect to zi, and then the ordinary derivative of zi with respect to s. Now, if you recall what we did in video number 9, this is how we went about defining our covariant basis vector. So that's all this is. So we can express this now as simply this factor, which is dzi with respect to ds times our covariant basis vector zi. That's just how we wound up defining our covariant basis vector. Now, as part of that analysis, we also learned that this whole expression is nothing more than the unit tangent vector for our curve. It's the unit vector that is tangent to the curve at point P. You might want to go back to video number 9 and refresh yourself on what we did here. Well, it's easy to see that this factor right here is the same as this factor. In other words, the vector that we're using right here in our dot product is nothing more than our unit tangent vector. Well, what about this vector? Well, all we can tell about it at the moment is that it's a covariant vector component. So if it's a vector and we want to represent it as a linear combination, we're going to have to do so with a contravariant basis vector. So let's just define a vector. We'll call it vector G for now, just to be a linear combination of this factor, the partial of f with respect to zi. And again, because it is a covariant vector component, we have to use the contravariant basis vector to define our linear combination. So what we're saying here then is that our directional derivative, this df ds expression, is just the dot product between this new vector g and our unit tangent vector s hat. Now, before we go any further, let's just quickly demonstrate that that's true. We said that our vector g is equal to the partial derivative of f with respect to zi times our contravariant basis vector zi, and we're going to dot that with the expression for our unit tangent vector, which is, and I can't use the same letter here because I'm already using I, so I'll use dzj with respect to ds times the covariant basis vector zj, like this. Well, the dot product between zi and zj is nothing but the Kronecker delta, so we'll have the partial of f with respect to zi times dzj with respect to ds times delta ij, and the delta function will absorb the j index, leaving us with the partial of f with respect to zi times the ordinary derivative of zi with respect to ds. And of course, this expression is the same as this, which means that this is the correct expression for our directional derivative. Okay, well now let's suppose that we have a second path, like this purple one I've drawn. It's a path through point P. So we want to figure out what the directional derivative is as the point passes through this curve. And we'll use u as our parameter this time. Well, we just go through the same analysis we did. We'd take the derivative of df, this time with respect to u, and we'd start with the partial derivative of f with respect to zi, and then the ordinary derivative of zi with respect to u this time. Okay, and then if we did our analysis on our position vector, we'd take dr with respect to du, and of course we'd go through the same kind of steps you see over here and ultimately realize that this is equal to our unit tangent vector along this new curve. Well, the point here is that our analysis led us to use exactly the same vector here that we have here. What's different is this factor. We have a different unit vector to work with, but we have the same vector right here. that means that the expression for the directional derivative along this new path is going to resolve to this. It's going to be df du is going to be equal to g. This is the same vector in both cases, but what's different is that we're dotting it with a different unit vector. And that makes sense because this time we're going through a different curve, so there's a different direction. Now we said in the beginning that the directional derivative up here is something that is dependent upon not only the function, but the direction we're moving. And that makes perfect sense because the way the function is changing out here may be well different than how it's changing out here. So we don't expect this expression to yield the same result as this one because we're moving to two different areas of our scalar field here. But both of these start with a common factor of this new vector g. And this new vector g is not dependent on the direction at all. So this is a common starting point for both expressions. And then we just dot it with the direction that's appropriate for either one. Now, each of these are unit vectors, so that means the only difference between these two is the direction that is represented by the dot here. All right, so because both of these depend on this common vector that we're talking about, that leads us to the following very important new definition. Now what I've defined here is a function that we call the gradient. Now the gradient is a function denoted by this symbol that operates on a scalar function. And the function produces a vector quantity right here. Now the vector that it produces is nothing more than the vector we've been working with right up here, this vector g. Now I'll remind you that the covariant derivative of a scalar function is equal to the partial derivative of that scalar function with respect to the same variable. No, so these two are always equivalent in every coordinate system. So we could just as easily have used the partial derivative here in the definition. But in keeping with the spirit and syntax of tensor calculus, we want to use the covariant derivative instead of this partial derivative up here. But it does mean exactly the same thing. Now notice also that I've defined it two different ways. I've used the covariant derivative here in combination with a contravariant basis vector, and I've also defined it in an alternate way as the contravariant derivative joined and contracted with a covariant basis vector over here. So in both cases we have a contraction, and therefore this is an invariant relationship. Now one more important thing, when you see an expression like this and there are no parentheses involved, it is implied that this is what we mean. The derivative operation applies only to the first term unless the parentheses are included to indicate otherwise. So if we wanted to show that this was a covariant derivative of this product of terms, we'd have to put parentheses around it like this. But without the parentheses, it means that we're operating only on the first factor in each of these expressions. All right, now what the gradient does for us is that it allows us now to calculate or quantify our directional derivative, this df/ds function up here, as a simple dot product between the gradient and the unit tangent vector that points in the direction where we're measuring our directional derivative. So it gives us a very simple and concise way to express the value of our directional derivative. Now let me point out a couple of observations we can make about this expression. The first is this, that when we have a dot product like this, its maximum value is realized whenever the vector here is parallel to this vector. Whenever s hat points in the same direction as the gradient, then the angle between them is 0, and there's a cosine theta factor here. So when theta is equal to 0, it's equal to cosine theta is 1, which is as great as it can be. So the direction of s hat in which the greatest value of our directional derivative occurs is that in which the s hat points in the same direction as the gradient. In other words, the gradient itself points in the direction of the greatest increase of our function. It points in the direction of the greatest directional derivative. Furthermore, when that's true, when this is parallel to this, then the cosine of theta is 1. The magnitude of this vector is 1, so the value of the dot product is simply equal to the magnitude of the gradient, which again is equal to the maximum directional derivative that we can have at that point. So we can say this, that the gradient points in the direction of the greatest directional derivative, and its magnitude is equal to the directional derivative value in that direction. Now I'm going to define yet another function that is closely related to the gradient. And we call this operation the Laplacian. Now the Laplacian is nothing more than a scalar function that is the divergence of the gradient. If you look closely here, this term, this expression, is just the contravariant vector component of our gradient. So we're taking the covariant derivative of the contravariant vector component of the gradient. And as the alternative, we're taking the contravariant derivative of the covariant tensor component of the gradient up here. So it's just the divergence of the gradient, and that produces a scalar function. Whereas the gradient itself produces a vector quantity, this produces a scalar quantity. Now, we denote it with this symbol, with the del squared. And the reason is because it's actually a second order derivative expression. We're taking two different derivatives, one after the other. So this is going to result in a second order relationship. Okay, with all of that, let me take a break here and give you a short demo with the graphing software. Here we have a scalar field represented in a two-dimensional space. And I've got a point here that I can move around the space like this. And we can explore what happens as we move to different locations. Now, I'll also define here a unit vector like this that I can rotate in any direction. So we can explore with that. I'll also add on an array here that points in the direction of our unit vector like this. Now let me add a label that shows two things. First of all, it shows the value of the scalar field itself at this particular point. So the scalar field has a value of 1.36 at this point. And the directional derivative is what we're showing here. The directional derivative at this point, evaluated in this direction, is negative 1.22. Now let me start by rotating the direction of our unit vector here, and notice that the value of the directional derivative changes depending on the direction in which the vector is pointing. Now, the value of the function itself hasn't changed, but the directional derivative does change. Here the value of the function is increasing in value. Here it's decreasing in value like this. Okay, let me move around a little bit, and you can see that the value of our scalar function changes as I move around like this. Let me set it on a point that's almost equal to 2 here. And now let's rotate the ray until the directional derivative reaches a maximum value. That's going to be somewhere like right here. Looks like about 1.54. Here it's decreasing in the other direction. So the maximum value of our directional derivative looks like 1.54 at this spot. So let's now display the gradient. And you can see this red vector is the gradient, and indeed it points parallel to the direction of our unit vector at this point. So the gradient points in this direction at this point and has a magnitude of 1.54. Now if I move the direction of our unit vector, the gradient doesn't change. The gradient is pointing in the direction of the maximum increase, and that would be in this direction right here. Okay, now let me add the contour so we can get a better feel for what's going on here. One thing you're going to notice is that the gradient is at right angles to one of our contour lines. And that makes sense because as we're climbing at the maximum rate, we're going to be crossing these isometric lines at right angles. Think of these lines as altitudes, as if we're measuring an altitude on a map. So here we're climbing up a hill as steeply as possible. Now if I move my direction, here we're climbing up as steeply as possible, but if I move over like this, we're basically walking around the hill. We're not increasing or decreasing. So the value of the directional derivative when I get parallel to our isometric line is going to be 0. And here it's going to fall off going in the opposite direction at the maximum rate like this. Okay, let me take these guys off and let's just look at what happens to the gradient as we move it around. Notice the gradient always points in the direction of the greatest increase. Now when I get over here, notice how much larger the gradient is than it was on the other side. And the reason is that over here, we're climbing the hill more steeply. The isometric lines are closer together, and therefore we're climbing at a steeper rate here. If we move over in this direction, the dashed lines represent the areas in which we're negative, so we're climbing out of a well here, climbing up to the outside. But here we're climbing up the hill to the peak. All right, and finally, let's take that off, and I'll add the vector field. This is all the gradient values just kind of represented throughout. And if we wanted to talk about the Laplacian would be the divergence of this vector field. So at this point right here, we'd expect the divergence to be as positive as can be because all of these vectors are pointing out from this spot. So the divergence is going to be very positive here. At this spot, it's going to be very negative. And so that would represent the Laplacian, would be the divergence of this vector field. All right, so hopefully that visual demo enhances your understanding of the gradient and the Laplacian. So let's conclude the video with a brief review. Now what we did in this video was to define a new operation called a gradient, and we denote it with this symbol. And the gradient operates on a scalar function like this to produce a vector. Now we define the vector it produces in one of two ways. It's either the covariant derivative of our function combined with a contravariant basis vector like this, or it is the contravariant derivative of the function combined with a covariant basis vector like this. The two will produce exactly equivalent results. Now with this definition, we can now express what we call the directional derivative according to this equation. The directional derivative, the rate at which the function is changing in a particular direction, is equal to the gradient that we just defined up here, dotted with the unit tangent vector that defines the direction in which we're measuring the directional derivative. Now we said that the gradient itself points in the direction of the greatest directional derivative and that its magnitude is equal to the derivative, the directional derivative in that direction. So the maximum value of our directional derivative occurs when the gradient points in the same direction as our unit tangent vector like this. And then finally we defined another operation called the Laplacian, which this time is a scalar function. The gradient produces a vector quantity the Laplacian produces a scalar quantity like this, and it's denoted by this del squared symbol, operates upon our scalar function, and it produces a scalar quantity. Now we use the del squared term because we're going to produce a second order derivative expression here. We're taking two different derivatives, one after the other, so the result is going to be a second order derivative. Now let me point out how useful and convenient our new definition for the contravariant derivative is. Notice that we pair a covariant derivative with a contravariant derivative like this. They can be done in either order, produce exactly the equivalent results, but because of the expression, we can clearly see that what we have here is a full contraction either in this direction or in this direction. So that proves to us that what we have here is an invariant relationship. Alright, in the next video we're going to take a look at what the gradient looks like in each of our sample coordinate systems.